Hello everyone, welcome to this new video of our mathematics. After a long while we are back to our channel. Around 3 months have been gone since our last video. So in today's video, as you can see on the screen, we'll try to solve some PhD entrance exam questions of Kansas University, Ohio. And in today's uh, video, we will try to solve one question. And there are more videos coming up. So please subscribe to our channel and uh, press the bell icon for notifications. Okay, so let's see the question paper. So here is the question paper. As you can see, there is a qualifying exam in algebra from August 2022. There are 18 problems on this exam. You have to work and turn in 10 problems. Okay. So you have to do only two problems from the ring theory portion, one from the linear algebra, three from the group theory, three from the field theory, and one problem from any of these four areas. Okay, so let's see the ring theory portion. So the questions are: let R be a commutative ring with identity. Let X belongs to R be a non-nilpotent element. Prove that there exists a prime ideal P of R such that X doesn't belong to P. Then there are four more questions. You can see all of them. There is this second question, that let R be a commutative ring with identity. We have to show that if X and Y are nilpotent elements of R, then X plus Y is also nilpotent, and the set of nilpotent elements is an ideal in R. All right, so let's do this question. Okay, okay. So as you can see, the question is, I will write down the question. It's given that R is a R is a commutative ring with unity. Okay. R is a commutative ring with unity. CRU. X and Y are nilpotent elements of R. Firstly, we have to solve. Yeah, for the software, we show that X plus Y is also a nilpotent element of R. Secondly, then we have to show the set of nilpotent elements, that is, say, N small r belongs to R such that R to the power M is say identity is 0 for this ring, say, for some M belongs to, okay, sorry, that, okay, so this set is an ideal of R. All right. So is it given? It is given that X and Y are nilpotent elements of R. What does this mean? That means there exists n comma n, say n certain natural numbers such that x to the power n is equal to 0 and y to the power m is equal to 0. So if we have to show that x plus y is also an input element, basically we have to find a natural number for which x plus y to the power this number will result in the identity element of the ring. Okay, so let us consider x plus y whole to the power n plus m. Alright, so what is this? If we use in a binomial theorem over it, or just uh, opening the brackets, we will arrive at? We will arrive m plus m c0 plus m plus n plus m c1, so n plus m minus 1 y, so on and so on, up to n plus m c n plus m x to the power 0, which will be basically the unity of this string times y to the power n plus m. All right. Now, so what is this? Basically, this is summation k is equal to 0 to n plus m plus m c k x n plus m minus k y k. All right. Now, without loss of generality, we may assume that n is greater than or equal to m. Then let's mark this as 1. Then 1 can be marked, can be rewritten as, or we can rewrite it as x plus y whole to the power n plus m, which was summation k is from 0 to n plus m, n plus m c k x to the power n plus m minus k y to the power k. This can be rewritten, we can break it. Okay, alright, let's see here. X to the power n is 0, y to the power m is 0. Alright, so here the power of x is decreasing. Alright, as long as this power is greater than x's power in the sum is greater than or equal to. In each summand, this power is greater than or equal to n. It will result in 0. Similarly, as long as this k is greater than or equal to n, sorry, greater than or equal to m, then this will become 0. Alright, so what we can write it as k is equal to 0 to m n plus m c k x to the power n plus m minus k y to the power k plus summation k is equal to m plus 1 to n plus n plus m c k x to the power n plus m minus k y to the power k. Now, here you can see k is from 0 to n. Alright, so this power n plus m minus k. Alright, so the maximum value k can attain is m. So this will always be greater than or equal to n. Alright, here. And for this part, k's power is always greater than, k's value is always greater than or equal to m plus 1. So here, this power is always greater than or equal to m plus 1, which is actually greater than or equal to m. Now, that means, what does this mean? This means for each of these summands, this value will be 0. Alright, x to the power n plus m minus k will be 0. Since x to the power n is 0, any power more than n will also result in 0. So this would be 0. And since we are in a ring, if this is 0, this power, sorry, this product is also 0. So all these summands will be 0 because of the fact that x to the power n is 0. Similarly, this summands will also be 0 because the fact that y to the power m is 0 and y's power is greater than or equal to m in each of these summands. So this will result in 0. That is, we have n plus m in natural numbers such that x plus y for n plus m is 0. That is, x plus y is an x plus y is a is a nilpotent element of R. Alright, now let's quickly move on to next part. This part says the set of nilpotent elements of the commutative ring of unity R is an ideal of R. So the set N, say A belongs to R such that A to the power N is 0 for some N belongs to N. This is basically nothing but an ideal of R. Alright, so if we have to prove that any subset, right, clearly N is a capital N is a subset of R. Any subset of R is an ideal. What we have to prove? We have to prove two things. As we know that uh, A minus B belongs to N for all A and B in N. And secondly, we have to prove that AR belongs to N for all A belongs to N and R belongs to capital R, and RA so also similarly belongs to N for all A belongs to N, R belongs to R. But since R is a CRO, AR is equal to RA. So it is sufficient to prove this part only and this part only. Alright. Now for the first part, let A comma B belongs to N be arbitrary. Then clearly there exists N comma M belongs to N such that A to the power N is 0 and B to the power M is 0. Consider A, uh, consider A minus B, sorry, not A plus B. Consider A minus B to the power N plus M. Then this is nothing but summation K is equal to 0 to N plus M minus 1 whole to the power K, A to the power N plus 1 minus K, B to the power K. Alright. Now, as we have done in previous portion, we can break it as K is from 0 to M, N is greater than or equal to M. With the loss of generality, we may assume this. Then this will be minus 1 whole to the power K, K to the power N plus M minus K, B to the power K, plus summation K is from M plus 1 to N plus M minus 1 whole to the power K, A to the power M plus M minus K, B to the power K. This will be 0 because of the power of A is greater than or equal to N here, and this is 0 because the power of B is greater than or equal to M here, which will give 0. That is, M minus B is a nilpotent element. That means M minus B belongs to M. Whereas A and B were arbitrary. So M minus B belongs to N for all A and B in N. Alright. Now for the second part, let A belongs to N be arbitrary and sorry. R belongs to RB arbitrary. All right. A belongs to let A belongs to N be arbitrary, and R small r belongs to capital R be arbitrary. We have to show that AR belongs to N. That is, AR is a nilpotent element of this ring R. So since A belongs to N, A is an nilpotent element, that is, thus there exists small n belongs to the set of natural numbers such that A to the power N is 0. Let us consider AR to the power N. Since uh, capital R is a commutative ring, this will break as A to the power N, R to the power N, since R is a commutative ring. Then this will become 0 times R to the power N, which will be 0 since R is a ring simply. Okay. So that is, there exists small n belongs to the set of natural numbers such that A to the power N is 0. That is, or that is, R is a nilpotent element, which means R belongs to N. And since A and R both were arbitrary, this is true for all A in N and smaller in R. Thus, N is an ideal of R. Hence, we have proved that the set of nilpotent elements in a commutative ring with unity, capital R, is an ideal of this ring. Also, if two elements are nilpotent, their addition in this ring is also a nilpotent element where capital R was a CRU. Alright. So this was the question and this was the proof of this question. I hope this is clear to all of our viewers. And with this, I end today's video and we'll meet in the next video very soon. Till then, bye bye.